Today we are going to discuss, dear students, I welcome you for the today's lecture related to the stresses in the chemical equipment design. The stresses is the most basic concept required for understanding of this subject, where we are going to design the mechanical aspects for a reactor. Generally, we are having the reactor a cylindrical shape, either of this type or this type. Now, from this cylindrical shape, I am going to have a section of that. From this cylindrical section, I am going to have a cut a small piece, and this can be shown here with the stresses, the principal stresses in the pressure vessel. They are to be taken into account. That is, one is the circumferential stress, which is also called as the hoop stress or tangential stress. Second, the longitudinal stress or the axial stress. And the third, the radial stress. So these three stresses, which are considered to be the basis for the analysis or the stress analysis of the chemical equipments or chemical pressure vessels. So understanding of these circumferential, tangential or hoop stresses with the addition of longitudinal and axial stresses is very much essential for this subject. Now, considering the one part, now if this is the plate and we are having the cylindrical section with this, so we are having the cylindrical section with this, and out of that we have cut a small section from here. So we will do the analysis related to that. One is the F1. It is sometimes also called as the sigma 1, that is the circumferential or the hoop stress. Sigma 2 or the F2, that is called the longitudinal or axial stress, and the F3, that is called the radial stress. So understanding these three stresses is very much essential for this subject. Now, while designing, we need to analyze this pressure vessel in two categories, that is the thick wall vessel and the thin wall vessel. We have already defined the relationship between the wall thickness to the vessel diameter. That is, depending on the ratio of wall thickness to the vessel diameter, the thin wall vessels as well as the thick wall vessel, they are classified. For thin wall vessel, the ratio of wall thickness to the vessel diameter, that is 1:10, and if it is less than 1:10, then it is considered to be the thin wall. If this ratio of wall thickness to vessel diameter is greater than 1/10, that is considered to be as the thick wall. So you need to understand the thick wall and thin wall, and you need to understand the three different stresses, and in addition to that, how we are going to apply it for a spherical as well as the cylindrical vessel. So that we are going to understand today. The principal stresses acting at a point in the wall of the vessel due to the pressure load. So this is the stresses that are being developed because of the pressure. Now, if you are eating and got a gas within you, gas within the stomach, then generally we feel stresses on the stomach, and these stresses that will be of the all three different types, that is circumferential stresses, longitudinal stresses, as well as the radial stresses. And that is what the pressure, the internal pressure, developed internal pressure is going to have the stresses. Even in case of a balloon, when you blow the air inside the balloon, that balloon gets expanded, and when you take out the air, that balloon again gets to its original shape. Because of its elasticity, it attains the original shape. Now, when we are talking about these stresses, if the wall is thin, the radial stress F3, if the wall is thin, this radial stress F3 that can be neglected. So F3 calculation for a thin wall vessel are 0. Radial stresses are 0 in case of a thin wall vessel. Only the circumferential and the longitudinal stresses will exist in a thin wall vessel. However, in case of a thick wall vessel, all the three stresses, that is circumferential, longitudinal and radial stresses, will exist. And that is why we have classified it into the thin wall and the thick wall depending on the wall thickness to the vessel diameter ratio. So if the wall is thin, the radial stresses F3 will be the small and can be neglected in comparison with the other stresses, and the longitudinal and circumferential stresses F1 and F2 can be taken as constant over the wall thickness. They are considered to be the constant when it's a thin wall. Now, in case of a thick wall, the magnitude of radial stresses will be significant and the circumferential stresses will vary across the wall. That we will see in the subsequent class. The majority of the vessels used in the chemical and allied industries are classified as the thin walled vessels. So generally we will try to analyze how the stresses they will be developed inside the vessel because of the internal pressure. One is the longitudinal stresses F1 or sigma L, then the tangential stresses or the hoop stresses or circumferential stresses, that is the sigma theta, and third is the sigma r or Fr, that is the radial stresses. So cylindrical pressure vessels, that is the hydraulic cylinder, shafts and the components on gear, pulleys, then barrels, then pipes carrying the fluid at a high pressure, and your cylindrical pressure vessels all will be exposed for these different stresses due to the internal pressure. So a pressurized cylinder is considered to be the thin wall T. In this ratio is in terms of the T and R instead of T and D. Now I am going to cut this cylindrical vessel in two ways. One is in this section and another is in this section, so that I will have this section, the stresses I can observe this section, and the another one is this section. When I have cut this from the one center, then I will see this section, right? And that is what is shown in the figure. When I am going to cut this in this way, I will be able to have observed this section and the corresponding stresses related to this section. And second way, I have cut in this section, then I will be able to observe this section. So one by one, we'll try to understand it in a different way now. Now, I am holding the tank or the vessel in this way or in this way. The stresses remain will be this one and the same. ऐसे पकड़ू मैं या ऐसे पकड़ू? Now I have hold the vessel as shown in the figure in the horizontal way, and I am going to cut through this section. That is also because of this, the internal pressure, the longitudinal fibers in the vessel will tend to stretch. When I have cut this, I will be able to see this part. I will be able to see this part. And this is what the longitudinal stresses that will be developed. Now I am pulling this in this direction. ऐसे horizontally खींच रहा हूं मैं दोनों साइड से, so that the stresses they will be developed are in the longitudinal direction. Now whether I am holding horizontally or whether I am holding vertically, but my pull is in the same direction. ऊपर में खींच रहा हूं यहाँ पे. The stresses developed in the vessel will be the longitudinal one. इस डायरेक्शन में स्ट्रेसेस डेवलप हो रही है. मैं वेसल ऐसे होल्ड करूं या वेसल ऐसे होल्ड करूं. So that is what the longitudinal direction or the axial direction, because it is considered to be as an axis of a cylinder. So whatever the axis of a cylinder that is there, when I am cutting it perpendicular with that, when I have cut the axis of a cylinder perpendicular, then that is going to give me the longitudinal or axial stresses. So because of this internal pressure, the longitudinal fibers in the vessel will tend to stretch and create a tensile stress sigma 2, that is called the longitudinal or axial stress. This stresses when I am cutting with this plane, sigma 1 and sigma 2, that is shown in this figure. So that I will be able to observe this figure when I have cut it like this. So you can observe this section and the corresponding stresses that will be there. मैंने इसको ऐसे खींचा है, that is nothing but your longitudinal stresses, or you can pull like this also, longitudinal stresses around its axis or parallel to its axis. The stresses develop parallel to its axis. The longitudinal stresses sigma y or sigma 1 is then obtained from the free body diagram. That is what is shown in the figure. Now one can take the balance over this. The stress balance and the pressure balance, that is the sigma 1 and 2 pi RT, that is pi d into T. This is nothing but pi d into the thickness. Now when I have observing this section, how I am going to calculate the area for this? That is the pi d into the T. This area is nothing but the pi d. Pi d is your circumference. I have opened it. This length will be the nothing but the pi d into the thickness. Pi d into the thickness. This is what? The pi d into the T. And that is being balanced by the pressure which is acting on this surface, this circumference के ऊपर अंदर के एरिया में जो एक्ट हो रहा है, that pressure, that is p pi r square. So by simplifying, you will get this sigma 2, which is p r upon 2t. This is also equals to the p d upon 4t, which is nothing but equals to the p d upon 4 into the thickness. So this is what the stresses, longitudinal stresses or axial stresses. These are called the longitudinal or axial stresses. So this is my formula for the stresses, that is PD upon 4T. This is already, you have studied it in the subject of strength of material. This is only the revision what we are trying to do. So this is the stresses, longitudinal stresses, and this is your pressure area that will be the exerted. So after simplification, you will get the equation. Then the next is the circumferential stresses or the hoop stresses. Now in this section, I have cut the cylinder in this direction, vertically cut कर दिया है इसको, and the stresses that will be observed vertically cut करने के बाद में कैसे दिखेगा, ऐसे दिखेगा वो, and that is what is shown in this concerned figure, is shown in this figure. So this is the hoop stresses, that is what is shown. So the exposed area will be this and the corresponding exposed area will be this one. So this is the circumferential stresses or the tangential stresses or the hoop stresses. This consider the thin wall cylinder vessel which is subjected to the internal pressure P and assumed to have the closed ends. A result of this pressure, the circumference of the vessel will expand. When I am providing the pressure, internal pressure over this, what will happen? This circumference will try to expand. This circumference will try to expand. And as a result, the stresses that will be developed on this section, when you will say the stresses will be developed on this section, That is what I am pulling like this. That is the circumferential stresses. When I am pulling like this, it will be considered as the longitudinal stresses. These are your longitudinal stresses. These are your circumferential stresses. Because I am having the internal pressure inside this. This internal pressure is going to give the stresses in this direction. It is being pulled like this. ऐसे कुछ तो खिंचाव डेवलप हो रहा है, स्ट्रेस डेवलप हो रहा है इसमें. And that is what you can observe the circumferential stresses when I am pulling like this, and the axial stresses when I am pulling like this through this axis. The figure I can shift like this, or the figure I can shift like this. So the result of this, because of the internal pressure, the circumference of the vessel will try to expand, which is going to cause the tensile stresses sigma 1 tangent to the circumference, and they are called as the hoop stresses. So I hope you have understood the hoop stresses, which will be in this सरफेस एरिया. कौन से सरफेस एरिया में डेवलप हो रही है, दैट इज ऑफ मोर कंसर्न. And here the projected area that is considered as shown in the red. So taking the balance over that, that is the thickness into the dy into the sigma 1 minus, which is equal to the p into 2r into dy. So the tangential or the circumferential stresses or the hoop stresses, which is equal to pr upon t, and this is nothing but equal to the pd upon 2t, pd upon 2t. So these are your circumferential stresses or the hoop stresses. So the hoop stresses, and which is being given in this section of sigma t into the length into pda into the length. So hoop stresses, that will be equals to the, so sigma L, that is the longitudinal stresses, which is equal to the half of the circumferential stresses. So the thin walled pressure vessels, the most commonly used type of the thin walled pressure vessels are cylindrical and the spherical vessel. So we will develop the stress equation. For that we have already developed it. Okay, so one by one we will write the circumferential or the hoop stresses, which is equal to the sigma theta, which is equal to pd upon 2t, and the longitudinal or the axial stresses, which is nothing but fa or sigma a, which is pd upon 4t. Now what is the p, what is d, what is t? P is the design pressure. The term P, that corresponds to the design pressure, and which is nothing but the actual or the operating pressure multiplied by 1.1 times. That will be equals to the design pressure. So whatever the pressure that is given in the numericals, we have to first study that whether it's actual pressure or the operating pressure that is mentioned. If it is mentioned as the operating pressure, then we have to multiply it by 1.1 to obtain the design pressure. Or else some numericals, they will be already given the design pressure. Then we are not going to multiply it with the 1.1. So the formula that incorporates this P as the design pressure, and design pressure will be equal to the actual pressure multiplied by 1.1. This is what we have already discussed in the previous class, where D is the mean diameter of the vessel. Now when D we are talking as the mean diameter of the vessel, that is nothing but the internal diameter plus thickness. Di is the internal diameter of the vessel, and Do, that is the external diameter, which is nothing but Di plus 2 times the thickness. So the D is there, the average or the mean diameter. Di is my internal diameter, which is taken into account, plus the thickness. This is the thickness, and the inside is my internal diameter. So the cylinder, uh, T is the vessel thickness, and F, that is the stresses, Ft or sigma T, that is the different stresses. So the cylindrical thickness, when I am going to calculate, this is equal to PD upon 2T. And for spherical vessels, which is nothing but PD upon 4T. Now PD upon 4T, that is nothing but your longitudinal stresses that will be there, and this PD upon 2T, that is nothing but your circumferential stresses. Then we have to add the joint efficiency in this case. J is the joint efficiency. So thickness, that will be is equal to PD upon 2Fj. And for the case of a spherical vessel, the thickness, which is equal to PD upon 4Fj. So cylindrical vessel thickness, which is equal to PD upon 2F, and for spherical vessel thickness PD upon 4F. Joint efficiency J, that is added. Now substitute this D as the Di plus T. Substituting this D as Di plus T, and try to simplify that, you will get the thickness, which is equal to PDI upon 2Fj minus P. And you can also substitute the average diameter D as Do minus T. Do minus T. This is what? D is the average diameter or the mean diameter. The above equation, that is thickness, which is equal to PD upon 2Fj, you will get the thickness, which is equal to PDO upon 2Fj plus P. So this equation, in terms of the internal pressure, internal diameter, this equation. This equation is in terms of the external diameter. This equation is in terms of the average or the mean diameter. So thickness calculation with the internal diameter, that will be considered as this. Now the C, that is the corrosion allowance, that can be also added to this. So with the corrosion allowance, the thickness calculation, the thickness will be is equal to PD upon 2Fj plus C. C is the corrosion allowance that has been added. Generally, it is taken as the 2 mm, 2 millimeter thickness corrosion allowance that is generally added. If it is a highly corrosive, then you can go to the 4 mm also. but mostly it is 2 mm thickness has been added as a corrosion allowance. Then the thickness calculation with the corrosion allowance for the internal diameter. The previous equation, which is the same as PDI upon 2FJ minus P, that is modified plus C. Similarly, for the thickness calculation in terms of the external diameter DO. So I am having the thickness PD upon 2FJ, so that I will be simplifying it to obtain the value of the F, that is the stresses, which is equal to PDI plus T upon 2TJ. The thickness of the shell is therefore given by, that is PD upon 2FJ, which is nothing but equals to the PDI upon 2FJ minus P. This is in terms of the internal diameter. Then in terms of the external diameter, that is 2FJ plus P. So this is to be remembered. Now the stresses are applied to the surface of the vessel and therefore do not experience the shear stresses. If the stress element were taken on the inner surface of the cylinder, it will be treated as the three-dimensional element. Then the longitudinal stresses is exactly half of that circumferential stresses. Longitudinal stresses is nothing but PD upon 4FJ, and the circumferential stresses PD upon 2FJ. Then the stresses calculated apply only away from the cylindrical ends, the contents. Okay. One has to note that this pressure P is nothing but your gauge pressure, the difference between the internal pressure and the external pressure. This is the difference between the total internal pressure and the external atmospheric pressure. That is the gauge pressure. If the internal and the external pressures are the same, then no stresses are developed in the wall of the vessel. Only the excess of the internal pressure over the external pressure has any effect on these stresses. Internal pressure that creates these stresses in the body of the vessel. The sphere is theoretically the ideal shape for a vessel that resists the internal pressure. That is your soap bubble. That determine the stresses in the spherical vessel. It is cut on the vertical axis and isolated from the other sides. That is what is shown in this figure. And when you do the calculations, that is the longitudinal or axial stresses will be the same as that of the spherical vessel stresses. So because of the thin wall, the stresses is uniformly distributed across the thickness, the accuracy becomes okay. So this is PD upon 4T, the stresses will be the equilibrium of the forces in the horizontal direction that yields. It is obvious from the symmetry of a spherical shell that we would get the same equation for tensile stresses when the sphere is cut through the center in any direction. So the stresses that act tangentially to the curved surface of a shell are called the membrane stress. They are called because these are only the stresses that exist in the true membrane like soap films. Now when we will see the numericals that will be associated for the cylindrical vessel, spherical vessel, then the effect of joint efficiency, then the effect of corrosion allowance, then we will do the calculations with the mean diameter, with the internal diameter, with the outside diameter, with the operating pressure, and with the design pressure. And we are mostly calculating the thickness required for the vessel, which will be able to withstand the given internal pressure. We have to design the vessel, means we have to fabricate a vessel which will be suitable for developing or sustaining the given internal pressure. There should not be any accident while operating that vessel. So in short, when there is an internal pressure which is available, now if I am going to pull in this direction or in this direction, that is going to be in the axial direction of the vessel. This is the axial direction of the vessel, and it is going to develop the axial stresses in the vessel when I am getting pulled either this way or this way, the axial stresses that is being developed in the vessel. Now when I am going to have the internal pressure, that is the circumferential stresses will be in this direction, that is the circumferential stresses will be in this direction, it will be considered to be in this direction. This is the circumferential stresses. And the third, that is nothing but your radial stresses. They will be in this direction. Radial stresses will be in this direction and will be observed from this side to this side. That is your radial direction. Radial direction. This is my axial direction, the circumferential direction, and the radial direction. So one has to remember all these three stresses for a thin wall vessel as well as the thick wall vessel.